So thank you for being here. So actually, I'm not Fabrice of La Gamboa, and this is Serge Gratton, so that you all know. So actually today I'm filling in for Fabrice because he cannot make it. So please, like, don't ask me too questions that are too technical because I will just try to fill in for the shoe. Yes, like fill in for him, and those are big shoes like to fill.
So we are sharing this talk because we organized inside of Anity by chair, and a by chair is we put together our two chairs to work on issues that combine statistics and also physics and numerical analysis, and so we have this an organization where we try to share meetings with our students. So in total, 20 students are involved there. One PhD student, nine permanent researchers. So it's really a significant team for doing research, interdisciplinary research, and we produced a significant number of journal articles and conference proceedings. You want
So yeah, so I will first like start yes just by telling you and justifying like why like we're doing this like together, and this is a format that we got to and that was suggested at the beginning by Fabrice and Serge, and the idea was every 2 to 3 weeks like we would meet yes like the entire group, sometimes like 20 people in the same room, and we would be like taking round tables and talking about each person's like problems, and that actually so that was very beneficial for me for example, because for example I am a probabilist like in training, but then all the numerical analysis that was more present on the team of Serge, I was just asking for pointers, having students to sometimes like work to together, and for me like that was pretty important at the for Ani during Ani T1, because that actually allowed this onboarding to machine learning more easily. And then we would have a 1 hour talk by a member. We had sometimes 1 day workshops. So for the first one was organized in June 2021 by Pierre Boudier from NVIDIA. And actually, and that was pretty important like to us, because like the topic was actually like talking between ourselves. For example, so as I mentioned, I knew almost like nothing about like practical numerical analysis. I come more from from this world, so just exchanging pointers. And something that was key is that like in these two chairs, we always had very strong interactions with the industrial world. And actually like the goal of today's talk is more like to give you an overview of the problems like we did like as a group, and not really, like we will not get into the details, just show you various things, yeah, um, that we did. Okay, so the industry partners like we had were plenty. We had our fence, EDF and CEA. Actually, like we had like a lot of PhD like theses with EDF and CEA, because actually they have very similar problems with nuclear uh, reactors. On the one side for validating them, and on the other side for using them. So there's a big part here with the global sensitivity analysis, which will be two use cases. We had Atos, BRL, Airbus. And actually here I forgot some. I remember like there's Thales. And actually, like in order to be able like to make this sort of thing work, so here, so it's clear that the amount of topics like we had to deal with were extremely broad. So some things, yes, that was pretty clear, is that all people like in the industry have similar problems. For example, like the first thing is sensitivity analysis and code and computer code experiments. So this idea of always, you have a big code that takes a lot of time. You cannot run it like that many times. And in order to validate it, in order to know, yes, like what are the variables that matter. So you need, so there are like lots of black box statistical tools. And the main one is like the broad topic of sensitivity analysis. Sometimes like yes, like you had inputs from different sensors from different modes, from different speeds, from different backgrounds. So you have like here like the problem of assimilation, like having incoherent and heterogeneous data and putting them like together. Then you had also, optimization for machine learning, and this part, like, yes, like was more like driven like in the share of Serge. So methods beyond like first order, robustness, complexity analysis, and also on the other hand, yes, because of the nature of the industry, like in Toulouse, so there was always like a part involving solving physical equations, like in EMA. So that's so it's pretty broad, and actually it's like this forces us like to make a selection, and we'll make a selection. So maybe I'll present just like the people. So permanence: Thomas Pellegrini, Reda Chhaibi, Pierre Boudier, Asseli Megurol, Alfredo Orflabutari, Xin Zhang, and Corentin Lapère. The associate yes, like, members. So actually, it's like because of this breadth of topics, it's like we had people like join us like in a broader circle as time went, like to bring different specialities. So Agnès Lagnou for sensitivity analysis, Savi for time series, Costantino from geometry and topology. As a postdoc, we had Anthony Fillon and also a bunch of external collaborator. And this is the slide that actually just like shows you the amount of PhD students. So all these names are PhD students. I was not involved in the supervision of all of them. So Fabrice did actually quite a lot of work. And actually, so I was mainly involved in the PhD supervision of Virgile Foy, Damien Rémaud, Anirban, and Alexei. So here I'm taking the time of advertising the lightning talk. So Alexei, you saw yesterday, like this afternoon, there is Justin Reverdy. So the little star here means CIFRE. So that's a thesis in collaboration like with the company. And here, there's quite a big group here from CEA and EDF. So Louis Berry, Fawzia Kimi, Marwan El Idrissi, Jérôme Stanger. All these were CEA and EDF. We had some Clément Benès in an academic PhD, like doing sensitivity analysis applied like to fairness. The rest, as you see, were mainly industry. Balou is also EDF. Yes, and we had Sernier Daouda Pen, who works with the Continental. Vir works with Renault. Reverdy works with Liber, and actually, it's like this symbol here is to mean that we had, joint supervision. Like sometimes, like both chairs like work together. So this is why, again, like a reason for doing like this talk in a joint fashion. So I hope this makes sense, and I'll let Serge mention like his students.
Maybe briefly, so SADOC on optimization and so Theo is working with Liber on flow prediction of flow. So sorry, Valentin is on this. Theo is working with Atos on robustness for neural networks. Mathis also with Atos on prediction of in data assimilation. And so maybe you see all the name, and we should go to the maybe to the.
So the selection of topics, actually, so here like this is, we did a little too many things. So here we will tell you about exactly 4 things, 4 instead of, I don't know, 20. So like yes, like the first part is optimization. And
So what is data assimilation? Is you have a chaotic system, like atmosphere is a chaotic system, and you want to predict the state of the atmosphere, and usually you work in very high dimension, like 10 to the 9 variables. Those are huge problems, and of course you cannot do that if you don't exploit the structure of the system. And the structure would be finding some so now we call this a latent space, but in this in data simulation is called some form of reduction, of model reduction. So here we were able to design a method for data simulation that employs here the variational autoencoder to solve the problem, and also to do the uncertainty quantification. And this is usually the difficult part for neural network, is to be able to estimate the uncertainties that you have on your problem. And we did experiments on highly chaotic systems like the Lorentz equations that represented the chaoticities that we find in the atmosphere. And you see the result. And this was published in a journal on meteorology. We also here went further and reproduce a Kalman filter. So it's a mathematical tool where we try to estimate as a function the Kalman filter function using. So a Kalman filter is implementing this kind of transformation. So we managed to find neural network structures to do this, to implement those highly nonlinear transformation. And this was again published in a journal for atmospheric sciences. But we also work on problem involving physics or not, and we try to design a structure that is multi-scale, because if you work on large dimensional problem, you have to again use some structure, and a structure that everybody uses when solving a differential equation is that there is a structure in scale. You have low frequencies, high frequencies, and if you don't do that, usually you can't get an efficient method. The difficulty with neural networks is that those methods, they tend to satisfy the so-called F principle, and F principle means that you can only solve for low frequencies with those methods. So it's very important to find mechanism to be able to tackle all the scales, which is what we did here by introducing a mechanism to zoom in on the frequencies. And we did that in the framework of a new generation of optimization methods that we designed. So objective function-free optimization method. So we got something like 10 papers on this topic. So the idea is to solve non-convex problems without evaluating the function, because it is very noisy. So this is what we did in this, and here you have some results we obtained on difficult classification problems. And here you see basically the comparison between our new method, which is the method here in blue. So this is the accuracy curve compared to the best method very good method in machine learning, because it's hard to compare them all, but it's stochastic gradient descent with momentum. So we managed to have multi-level version of these highly used methods, and this is a very recent paper that we submitted and got accepted in the SciOpt journal.
So I will continue now. Yes, like with the part with the GSA, so global sensitivity analysis, like which was one of the main tools that was used by in many of the PhD supervisions and industrial use cases. So okay, so this is like an example from Serra. This is extracted from the thesis of Louis Berry. So I'm not like putting like all the names, because that would be too much. So that's so this one was made by Louis Berry, and the supervision was by Fabrice and Amandine Marel at Serra. So the idea is to understand why a code fails. And here, like typically, like the example here is, so you have a nuclear tank with the fuel, and the fuel is too hot, or the coolant is too hot, and it ruptures. So here you have some finite like element blocks, and then it tells you, okay, yeah, so it ruptures here, and then it leaks. Okay, so that's a code that actually is not very GPU friendly. Actually, this is a code that runs on multiple like CPUs, and that is very costly. And here they have a validated simulator called the MC3D, and it simulates and computes the interaction between fuel and coolant in severe nuclear accidents. And here, there's a typical problem is that like you have different parameters like temperature, pressure, model of the model and the year and the use of the nuclear power plant. And the problem is that a third of the runs fail. They don't. So, and the question is, why do they fail? And the question is, understand like the inputs which have the most influence on the code failure. Again, high dimensional problems. And here, like the methods that they used in the thesis of Louis. Yes, it was actually a condition like to code failure using goodness of fit test and dependence measures, which is again a topic in GSA. So another topic here was the calibration of a twin, or like so a digital twin of a nuclear reactor. So the idea here is that this is the thesis of Fauzi, of Akimi, I think. And so here's a schematic. So you have a simulator where in your simulator, like by default, all your nuclear rods are very well aligned. Like there's but in reality, like things have extra parameters that you need like to tune. You need like to find them, and you need to feed them to your simulator. And the problem is that like you're measuring them, and you need like to tune your simulator like to match the nuclear power plant that has been built, because for simple reasons, yeah. So there's 1,000 dimensions, and if you want just run like play once, so it's days on multiple like processors. So here like the challenge is clearly like that you need like to calibrate with a very minimal number of runs. So and the proposition is to use a Bayesian methodology to combine real measures and expert knowledge from simulators, and decomposing like the measurement as computer code, error from the code, error from the measurement. And without getting too much like into the details, so like the methodologies first break like the multiphysics into smaller pieces. Like the global simulator is is a sum of simulators, and actually like GSA is used like to actually try to understand which part influence less on what. Yes, like what is the range of influence of every part. So the sample recombination. So this is actually a part that I understand. So this part is actually a specific like methods from neutronics, and the idea. Okay, so if you have like multiple samples from parts that don't talk to each other, you can just like multiply them, right? But here, if they talk a little bit like to each other, you need not multiply them, but you need like to reweight, do some resampling, some Gersanov type things, and that's the specific ideas that actually, even in math, come from neutronics, actually. So I guess this is fair. And the result is the possibility of the calibration of a digital twin based on a small number of Monte Carlo simulation, and using like these methods of these neutronics method like to create a very big data set out of very few. So that's the general idea, and here you have a scheme. And finally, here I'm choosing like to put to honor, it's like another collaboration that was a bit transversal. So here, this is the thesis of Mehdi Douitine, who is supervised by Agnès Lagnou, Clément Pellegrini, and I think I've seen him somewhere, like Rachelson, Emmanuel. And actually it illustrates again like this philosophy of it's like when you meet someone, and actually so it's better to just go see like the people that work in this and do co-supervisions. So here the topic is reinforcement learning applied to satellite planning, and the objective is to explore deep reinforcement learning methods for COPS, combinatorial optimization problems. And the practical application here, I think it is with Thales. And the practical application is the scheduling of satellite constellation. And the idea is, so you have a bunch of satellites, and they pass, and yeah, so they can pass in certain zones of the Earth, and at a certain time, and there's some control, like they need to be somewhere at a certain time, right? And you need to plan who will go where, when. And this is a combinatorial optimization problem. And another part of the thesis is on top of the combinatorial optimization problem, aiming to develop tools to explain why this solution is proposed, and the so X plus AI agent behavior. So I think that's all.
Thank you, Reda. Okay. I don't know if there are questions. Yes. Yes. So, so the idea is to stretch the time scale in such a way, so get rid of the frequency you can solve for, so the low frequencies, and then you stretch the time scale in such a way that in the new system you get again low frequencies that you can solve for in turn. And to do that, you implement several networks, everybody taking care of a bandwidth of in frequency, and you solve in sequence for all of them. So it's quite close to a technical V cycle in multi-scale methods. Thank you. Yeah. So I don't know if there are more questions. Yes, you have a question.
I just, well, thank you again for the presentation. I hope this question is not too technical, but can you tell us more about you were talking about the dependence between the input and also studying its effect on the failure of the code. I imagine that you take the code as a black box function and you just play on randomizing or sampling the inputs to get some results on the output. But you know that the corner cases are very hard to get sometimes. The code is well done. The corner cases, or well, the cases where the code fails are hard to get. So do you have any strategy on how to sample the input and also how to act on different input spaces? Because sometimes you get to deal with discrete and continuous inputs, and what are your strategies or methods to do the sampling?
So actually I did not hear you very well, but I think I understand like the gist of the question. So I'll interpolate somehow points. And okay, so I guess like the question is, yes, okay, so actually like in all those cases, so here, so I guess like you were talking about this slide, and because like code failure, so in this case like happens quite a lot. So it's a third. So you can think of like a third of the parameter space has problems, and we would like to understand why. And the idea is that, so like a global sensitivity analysis, yes, it's just pure stats. So it's just like this idea of so you have a sequence of runs, the parameters, and did it fail or did it not fail? And the question is, so statistically, is there a causality? So it's more than correlation. Is there a causality between those? And there are like many indicator or statistical estimators of causality, so that tell you, okay, these variables matter, these don't, and you can do it purely statistically, like without, and actually like the function f complete black box. So the computer code, you don't even like have to look at it. And Fabrice actually even like wrote a book on this thing. So I exactly, so if you tell me, okay, give me methods of global sensitivity analysis, Fabrice like knows 10, I know 1 that I like very much, so I'm sticking to it, and maybe I can give you a reference for that one. Sobol indices.
Okay, so thank you very much. Yeah.